Well, in the previous video, I explained what's transformational about a linear transformation. Now we're going to explain what's linear about a linear transformation. So here's the definition. If V and capital V and capital W are vector spaces and C is a scalar, T, which is a function map from V to W, is a linear transformation when for all U, V vectors in V, and any scalar C, T of U plus V is equal to T of U plus T of V, and T of CU equals C times T of U. Now, I just want to make sure there are certain things which could be a little ambiguous here, and I'll explain what I mean by that. First of all, you see a plus here and a plus there, but these two pluses are not the same, because the plus over here is adding two vectors in the domain V. The plus over here is adding two vectors in the range W. So addition may be defined differently in the first vector space than it is defined in the second vector space. I'm using a plus and plus. I'm using the same symbol, but these are two vectors because U and V are vectors in the domain V, but TU and TV are vectors in the range W, or the codomain W. Similarly, the scalar multiplication is not the same because here I'm multiplying C times the vector U, and U is in my domain. Here I'm multiplying C times TU, and TU is in the range. So it's a different scalar multiplication, or multiplying a different vector, a different type of vector. In other words, U and V is in one world, TU and TV is in a different world. U and V are in the world of V, TU and TV are in the worlds of W, and the addition here is whatever way it's defined in the domain. Addition here is whatever way it's defined in the range. Scalar multiplication here is whatever way it's defined in the domain. Scalar multiplication here is whatever way it's defined in the range. And that's an important distinction to realize. Let's look at the example we did in the previous video. We showed how this takes vectors from R2 and sends them into R3. Well, let's see. So it is a transformation, but is it linear? Let's test it. Well, we have to test 1 and 2. So let's do it right now. Well, again, this is my A comma B, that's my U. C comma D is my V. And that's equal to, well, this, I could simplify this without doing any transformation yet. I'm simplifying what's inside the big thing. So this is really A plus C comma B plus D. And now I'm going to transformate that, which gives me the x value, which is A plus C, the y value, which is B plus D, and now the z value is just the sum of the x and the y. And now I'm just going to rearrange this. Well, I just have to rearrange this now. This big vector is actually a sum of these two vectors, but this vector is T of U, and that is T of V. So that's my T of U plus V is equal to TU plus TV. And now let's do the second property. If I have T of C times V, now, so U is that's like AB. So T of this, now I multiply the C into here. I haven't done the transformation yet. I multiply in here. And I get, now I do the transformation. So I get CA, CB, and CA plus CB. But I could just factor out the C. But when I factor out the C, that's C times T of AB. So we see that T of CU is equal to C times T of U. C times T of U is equal to C times CU. And here we go. Yay!